Hello everyone. This is Group 130, and we are presenting our final update on our neural networks project. So the topic of the project is comparison of various machine learning or deep learning models on detection of deep fake images. The group members are myself, Prathamesh Thakur, Harsh More, and Nantha. So moving on to the motivation and the problem statement. So as we know, Gen AI has become a huge thing in today's age. Newer and newer off-the-shelf models are available for use by anyone and everyone. And with APIs to current large language models as well, Gen AI has become very accessible to all. And the accuracy of the models is also increasing day by day. And that makes it more and more closer to human-generated content. And here's where deepfake technology comes in. So the deepfake simply means images, audio, or video which is generated using AI. So it is not real, but it is synthetic. It is something which is made using artificial intelligence. And deepfake technology has advanced rapidly with the advancements in Gen AI, and that is why the content generated by the artificial intelligence is becoming more and more human-like, which is making it much more difficult to distinguish between what is real and what is artificial intelligence. Deepfake techniques do have some useful applications, such as in the entertainment industry, where we can create frames using artificial intelligence and then improve the animation quality. But it also poses serious threats, which include some misinformation or identity theft or some fraud schemes. So the project tackled this problem by comparing various models, which can be used to distinguish between real and AI-generated images. So moving on to the data. So the data which we've used is publicly available from Kaggle. It contains about 15,000 images, and the input will consist of the images which are either real or AI generated. And after feeding it to the model will predict whether the image is human or AI generated. So this was our baseline model. So the baseline model consisted of a convolutional neural network, which was custom built. So specifically for this problem, this CNN was built. And as we can see that the architecture consists of some combination of convolutional layers, some batch normalization layers, and the max pooling layers. At the end, what we've employed is a linear layer of 512 neurons. And then the last layer is a sigmoid layer, which will predict whether the image is real or AI generated. There are two labels, 0 or 1. 0 indicates a real image and 1 indicates an AI generated image. So as we can see the performance in the classification report, we can see that the model performed around 85% accuracy. But if we see the confusion matrix, we can see that the real images which were predicted as such, but were AI generated is 221. So considering the test set, that number is pretty large. So what we tried to do is reduce this number in the further models.
So now considering what results we had obtained from the baseline model, the second model that we had used was the ResNet model. So ResNet model is basically a residual network that is a deep convolution network, neural network, which is like an innovation where there are residual blocks which skips connections and allow gradients to flow back more easily during back propagation. So basically, the ResNet 18, which is a variant of 18 layers, has been used in this project. So there is an initial layer which accepts images of the size 50 by 50, which we have taken in this project. And there are residual blocks that has various layers. And so we are considering a loss function of binary cross entropy. And at the end of the layers, there is a sigmoid function that is being applied. So as you can see, this is the flow of the layers that has been applied for the ResNet model. And as you can see, for the precision recall F1 scores, the accuracy was pretty close to the baseline model, that is up 89%. And the data set that was considered was same as 1500. So the number of real images that were predicted as AI generated was still pretty high as compared to the data set. So this model showed that it was this baseline model and the resonant model were pretty close to each other in predicting the images.
Yeah, then moving on to the third model which we tried was the Vision Transformer model. So the main good thing about this Vision Transformer model for image classification task is that it would be creating the patches of our input image, and then it would positionally encode each patch and then follow our traditional transformer encoder architecture for doing the image classification. So this is the architecture which we followed for this Vision Transformer model, and based on that, the results which we get, if you see at the classification report, you could see that the accuracy which we got was around 97%. Also, if you check the number of images which we used this model against to test was somewhere around 8,000 images, which is comparatively even more number of images which we use for testing compared to the baseline as well as ResNet. And over here, if you check the false positives which we got are just 142 false positives. So this is comparatively a better. The model was able to perform quite better compared to the other two approaches. So this is why we think that the Vision Transformer model clearly outperformed the other two models, giving some good accuracy as well as making some good quality predictions. Thank you.